Very good afternoon to everyone. So today we are going to see about economic load dispatch problem. That is one of the important problem in the economic operation of power systems. Okay. Now in the subject we are dealing with this optimal operation of the power systems. So in that one such important problem is that economic load dispatch problem. So how to define this economic load dispatch problem? So already we have seen enough about optimization techniques. So in that every problem has its own objective function and as well as the constraints that we have seen in our previous classes. So in the economic load dispatch problem also, it has some objective function and as well as the constraints. So objective function, the ultimate objective function of economic load dispatch is to minimize the total fuel cost. Minimize the total fuel cost. And also we have to optimally allocate the generating units. Okay, optimally allocate the generating units with all the constraints satisfied and also with the minimum fuel cost. We need to minimize the total fuel cost. And if coming to the constraints of economic load dispatch, there are two types. One is power balance constraints. So power balance constraints, that is nothing but generation that equals the demand. If we neglect the losses, okay, or otherwise generation is equal to demand plus losses, or generation that equal to demand. If we neglect the losses, this is the power balance constraints. And another one constraints also there, that is minimum and maximum operating limits. Minimum and maximum operating limits. That is, whatever the generation that is happening, that should be within the minimum and maximum operating limits. Okay, so the definition of economic load dispatch goes like this. Okay, like many of the students have asked about, sir, how to define this economic load dispatch in the 2 marks. So if it is asked in the 2-mark question, I think most of you you'll be studying the 2 marks in the last moment. Okay, so they are repeatedly asking, sir, how to define, tell me the easy technique of defining this economic load dispatch. So the definition of economic load dispatch goes like this: optimal allocation of generating units to the generating station. Okay, so optimal allocation of generating units to the generating stations with all the constraints satisfied. Okay, with all the constraints satisfied and also with the minimal total fuel cost. Okay, so minimum total fuel cost also should be minimum, and also we have to allocate the generating units optimally with all the constraints also satisfied. That constraints might be of your power balance constraints. Okay, so power balance constraint, how to define this power balance constraints is nothing but, so whatever the power generation that is happening, that equals the demand and also plus losses. Okay, sometimes only demand. If the losses is neglected, then it is only demand. If the losses also had added, then the generation that equals the demand plus losses. Okay, so demand is nothing but your load also. Sometimes whatever the load, that is called the demand. Okay, so generation is equal to demand and also with the losses. If you consider the losses, transmission network losses also there, you can also write transmission network losses. Transmission network losses. Okay, transmission network losses. Okay, so whatever the generation, that equals the demand and plus the transmission network losses, that is called your power balance constraint. And what is the next constraint? Next constraint is minimum and maximum operating limits. That is, whatever the generation that is happening, that is, we are going to find out the optimal generation, that is PGI, that should be within this minimum and maximum operating limits. Okay, so that is the next constraint. So this constraint, so already we have seen, no, this constraint, power balance constraint is nothing but your equality constraints. So equality constraints, okay. So equality constraints. This is called your equality constraints, and this minimum and maximum operating limits, that is called as your inequality constraints. Inequality. Inequality constraints. This is power balance constraints is nothing but equality constraints. Minimum and maximum operating limits is nothing but your inequality constraints. So okay, so if you find out, if you don't know what is equality constraints and inequality constraints and what is objective function, you can go through my previous classes. Okay, so it is, I have clearly explained about this, what is objective function, what is equality constraints, and what is inequality constraints. So if you are having any doubts in this, you can go through my previous classes. Okay, so once again, I'm repeating this economic load dispatch problem for 2 marks, 2 mark question. I think this might be your might be your first 2 mark in your midterm exam and semester exam. So definitely they might be connected with this question, or sometimes in your big question also you can able to write this kind of you have to define this problem. So economic load dispatch problem. Okay, economic load dispatch problem is defined as optimal allocation of generating units to the generating station with the all the constraints satisfied, and also with the and also we have to minimize the total fuel cost. Okay, so we have to minimize the total fuel cost and with the minimum fuel cost. Okay, this is the definition of economic load dispatch. And what are the constraints? Constraints is nothing but your power balance constraints. Power balance constraints nothing but equality constraints. Okay, so in exam you should not write only equality constraints. Okay, so in the optimization point of view, this term is called your equality constraints. So what is power balance constraints is nothing but, so whatever the generation that is happening, that is equal to your demand and as well as network transmission network losses. So sometimes if you neglect the transmission losses, so you can write like generation that equals the demand. So what is the next constraint? Next constraint is that inequality constraint. That is nothing but minimum and maximum operating limits. That is whatever the generation that is happening, that is whatever the generation that we found out. Okay, that is PGI. We can call it as PGI. That is power generation of ith generation. So that should be within this minimum and maximum operating limits. Okay, it should not go beyond this minimum, and it should not go beyond this maximum also. Okay, it should be within this limit. Say for example, the power generation you are going to find out is some 90 megawatt. 90 megawatt. The minimum and maximum operating limits given in the problem is 50 megawatt to the maximum of 150 megawatt. Okay, so 90 megawatt is within the minimum and maximum operating limits. Okay, so sometimes it may come like 150 rather than 150, it may come exactly like 150 also, or sometimes 140 also. So 140 also it is within the limit. Okay, so whatever the generation that is happening within the minimum and maximum operating limits. So if you write with an example, it is well and good for 2 mark question also. Okay, so generation you can take some 1500 megawatt, demand also 1500 megawatt. demand some 1450 megawatt. Then transmission network losses some 50 megawatt, or some 20 megawatt you can take, because 50 megawatt is more. So some 15 to 20 megawatt you can take. So 1480 megawatt as a demand, and network losses as 20 megawatt. So it is satisfying the generation. And also minimum and maximum operating limits. Say for example, the generation, it is happening, no, here it is generation happening 1500. So some minimum and maximum operating limits already given in the problem. So for example, you can consider like 1000 to 2000 megawatt. So here you can write like 1500 megawatt. So that is 1000 to 2000 megawatt. It is within the limit. Okay, it should not go beyond this value, and it should not exceed that value also. So it is in the limit. Like that also you can explain with a simple example. So how to define a general optimization problem and as well as the constraint. So what is optimization in the sense? The optimization is defined as minimizing or maximizing of an objective function subject to constraints. Okay. So sometimes, as I said, like the objective should be minimized. Sometimes the objective should be maximized. Okay. So we can define the objective function like optimization problem like this: minimizing or maximizing of an objective function subject to constraints. Minimizing or maximizing an objective function subject to constraints. So the constraints are of two types. As I already mentioned in the problem, the constraints are of two types. So one is your equality constraints. Another one is inequality constraints. Okay. So equality constraints. So whatever the resource value that equals to the functional value, that is called your equality constraints. So whatever that we have taken, that is utilizing. So that is called your equality constraints. Okay. So resource value that equals the function value. So inequality constraint is nothing but, so resource value is not equal to the function value, but it should be within the limits. So whatever the limits, okay, it is given, so that it should be within that particular limits. Okay. So that is called your inequality constraints. So similar to this, so we have to compare that optimization problem with our economic load dispatch problem. Similarly here also we have the certain objective function and as well as the constraints. Here the objective function is to minimize the total fuel cost. As I already said, minimize the total fuel cost, that is already I have said. So here the objective function is to minimize the total fuel cost incurred in all the generating units. Okay. Say for example, PGI, we are mentioning PGI. That is, PGI is nothing but power generation from the ith generating unit. Okay. So it might be from 1 to n. Okay. You can take the values of I from 1 to n. Either it may be 1, 2, 3, up to n generating units. Say for example, you are considering the I is equal to 100 generating units. So 1 to 100 generating units we are taking into account. So almost all the generation, so whatever that happening, so we need to minimize the total fuel cost incurred in the each and every generating units. Okay, not only first or not only 10th or not only 50th. So as a whole, like for example, if you have taken 100 generating units, as a whole we need to minimize the total fuel cost incurred in that. Okay, so the total fuel cost is directly proportional to your your tariff. Okay, so how much cost you are reducing in the total fuel cost incurred in all your power system operation, okay, and transmission and distribution. So that is how you will be charged with your tariff. If this raises, say for example, you need to select the optimal generators. Okay, so that is called the optimal allocation. So here the name itself, optimal allocation. So we are from the 100 generators. Okay, so you know the resource cost. Okay, resource cost for each and every generator. Say for example, generator 1. Generator 1, I'm saying about one example. For for producing one unit, per unit you are spending around some 20 rupees. Generator 2, you are spending around 15 rupees. Generator 3, you are spending around 10 rupees. Okay, so which generator you will choose? You will choose for generation. Okay, so definitely we'll choose the least cost, that is the per unit cost of generator around 10 rupees. Okay, so imagine three generating units are of thermal generating units. Okay, so first generator is somewhat farther from the your coal yard. Okay, so for coal, you need to carry that coal from the coal yard to that particular thermal station. Okay, it might be of 100 kilometers or 200 kilometers. So okay, transportation cost is there. Okay, so the cost of that particular per unit cost of that generation from the particular generating unit is 20 rupees. So another 15 rupees generator is somewhat nearer to your coal yard. Okay, so that is some 50 kilometers far. Okay, so you need to spend for transportation and everything, no? So approximately, while taking all the things in consideration, so it is coming around 15 rupees per unit. Okay, for generation. Okay, next, the third generating unit is somewhat nearer, maybe 10 kilometers far. Okay, so 10 kilometers far is very easy to carry. Okay, so that cost, the whole total cost for generation in that particular third generating unit is around 10 rupees. Okay, so which generator we'll choose? So we need to select optimal generators. So which generator we'll choose? So definitely that third generator with the lowest cost, so that the total cost, fuel cost of whole generator will be minimized. So say for example, from the 10 per unit, some 10 generating units are there. So we'll choose first that 10 generators. Based on the requirement, we'll choose this 15 rupees generator, and based on the further requirement, we'll choose the 20 rupees generator. But the first priority will be given to least cost generator. Then only the whole the cost incurred for the all the generation and allocation, everything will be reduced. Okay, so similarly, so this is the objective function of the economic load dispatch, that is minimize the total fuel cost. So constraints is, so as I said, power balance constraint. So from the name itself, power is getting balanced. Okay, from the name itself, you can define power is getting balanced. That is, so whatever the generation, so the resources that is equal to demand. So resources, that is whatever based on the resources we are generating. Okay, so that equals the demand, or otherwise load. We can tell the demand as load also. In other words, load. Okay, load plus losses, transmission network losses. Transmission network losses is always it will be there. Okay, so nowadays here transmission companies, they are claiming like we have reduced the so previously they told like 20% transmission losses. Next, after 10 years they told like only 18%. After 5 years they told like only 15%, and now they are claiming like 12%, and some places they are claiming like only 10%. Okay, say for example, 100 megawatt you are generating. Okay, at the remote user end, okay, at the user end, at the distribution end, you'll be receiving only 90 megawatt. Okay, so because 10% transmission network losses, so sometimes they will say like 12% network losses. Okay, so 12 megawatt you are losing as a transmission network losses. Say for example, some other transmission companies, they are claiming 15% transmission network losses. In that scenario, they are claiming like 15 megawatt as the, so only 85 megawatt only you will receive at the like receiving end, that is distribution end. So even though you can generate 100 megawatt, because it is transmitting for some kilometers, some 20 kilometers, 30 kilometers, or 100 kilometers, like that, the transmission will be there. So after that, at the end user end, okay, at the end user end, you will get only 85 megawatt or 90 megawatt, like that. because they're claiming 10%, 12% as a losses. So sometimes you'll get transmission network losses. Sometimes you'll get transmission network losses. Okay. But in the problem, while solving the problem, sometimes we'll neglect this transmission network losses and we'll solve the problem. Sometimes we'll add the transmission network problems and solve the problem. But practically speaking, definitely the network losses might be there. Okay, without the network losses, there won't be transmission. Okay, if a transmission is not, if a generating unit is very near to the load, so even though it has to go to that user end, no, say 2 kilometers, 3 kilometers, that 2 kilometers, 3 kilometers also you'll get minimum losses. Say for example, 5% losses, 6%. You can reduce the losses with the. So if a generating station is situated very near to your load, that is distribution end, okay, then that is called your distribution generation. That concept is different. Distribution generation and formation of your smart grid, that you are going to study, okay, in the forthcoming classes. Okay, so that so if the generate, but majority of the if you take like majority of the thermal generating units, it is located very far from the load station, that is a distribution system, okay, from the loads. Okay, it is if you take the radial distance or road distance, if you take or radial distance, if you take, it will be like 200 kilometers, 300 kilometers apart. Okay, so it has to travel from 200 kilometers to your house. Okay, that power through your substation. So definitely there might be some transmission network losses. Okay, without the transmission network losses, it might be not possible. Even say for example, if the generator is placed near to your house, say for example, it is placed 1 kilometer, 2 kilometer apart from the house. Okay, it is of very mini hydel generators. Say for example, mini hydel generators of some 15 megawatt or 20 megawatt or 30 megawatt. It is you're located near to a dam. Okay, near to the dam, whereas your mini hydel power plants also there. So you're located very near to that, maybe 2 kilometers, 3 kilometers apart. So in that scenario, the transmission network losses might be of some 5% or 2%, 3%, but there might be definitely transmission network losses. While electrons is passing through the conductors, definitely the heat losses might be there. Due to that heat losses, definitely the power electron losses might be there. That is power losses might be there. So definitely you will not get the same power, whatever the sending end is, whatever we are sending, you will not get at the receiving end. So definitely you will be having some network losses. So that is the concept of your power balance constraints. That is generation that equals the demand plus transmission network loss. So next constraint is that minimum and maximum operating limits. Okay, so whatever the generation that is happened should be within the minimum and maximum. Sometimes say for example, if you take the thermal generating unit generator, okay, so there will be some limit. If you take like 1000 megawatt generator, okay, so if you read the nameplate of the generator itself, okay, there will be some the conditions. Okay, there will be some condition. You have to run the generator minimum at this speed. Okay, minimum at say for example, sometimes the poles might be more, 6 poles might be there. So the if you note down the speed of that particular generator, okay, if you take the hydro, like hydel power generator, the poles might be of sometimes 6, 8, like that. Majority like 6. Okay, if you take the speed of that particular generator, it might be of only 200 rpm. Okay, 150 rpm, 200 rpm, because the generator size is more, like 100 megawatt. Okay, 100 megawatt, that turbine has to turn. Okay, so like the power, the potential energy. Okay, the potential energy what you have to give is more. You have to give very very more. Okay, so then only that the whole turbine will rotate. Okay, so it is not easy like as like your steam, because steam you're producing more power through the boilers. Okay, you have studied in your previous classes steam. You're having more power than the hydro. But even though hydro, that from that penstock, it has to rotate. That the whole turbine has to rotate. So more potential energy is needed. More potential energy is needed to turn that turbine. Okay, so minimum like 100 kilometer per hour to maximum of 150 kilometer per hour, that potential is needed to turn that runner, that is turbine. Okay, so then only the generation is possible. So if you note down the speed with the tachometer, if you note down the speed of that particular power station, so it might be of only 200 megawatt. It will not like 1500 megawatt as you do in your laboratory. Okay, laboratory generator alternators might be there, but that is coupled with your motors. Okay, if you take the in your machines lab, that generator is coupled with your motors. That motor is running at 1500 rpm. So similarly same, that is that shaft is being connected with your generator. So same, this generator also will run at 1500 rpm. Okay, in laboratory it is possible. Okay, for experiment purpose it is possible 1500 rpm. But in real world, practical world, 1500 you can, it is possible, but that much potential you need to give. Okay, so that much see, for generating 100 megawatt, you minimum you needed 100 kilometer per hour to maximum of 150 kilometer per hour. It depends on the size of the generators, and okay, like sometimes it might be 200 megawatt like that. So for generating 1000 megawatt, even with the same your hydro, so 5 times more you are needed. 5 times more you are needed. Okay, potential energy 5 times more you are needed. So that too, your speed will be like 200 only, 200 or 250, 150 like that. Okay, it is like very minimum speed only. Okay, but in the large scale, if you're running it might be generating more noises also. Sometimes if you see in the, if you stand in the hydro power station, you'll get more noises. You can't simply stand in while the generator is running, you can't stand near to the generator. Okay, so it will create more noises also. Okay, why? Because the generator size, you can see like it is more than your classroom. Okay, generate a size of that particular thing. If you take like the whole the size, if you take like, it's more than the classroom. Okay, so in the nameplate they will get, it should not you should run that particular generator within this speed only. Okay, you should not go beyond that speed. And so maximum speed also will be mentioned in that particular generator itself. Say for example, some 300 rpm, like I'm talking about 100 megawatt. 100 megawatt, it should not cross around 300. If you cross the 300 rpm, automatically your shaft and all, everything will break out. Okay, you can go. Why? Because you're giving more pressure onto that particular generator, means automatically you're like horse riding only. Okay, so if you're giving more thing to that horse, okay, there will be some maximum speed of the horse. Okay, maximum speed of the horse. So watt calculation, you know the watt calculation, how horsepower, we are calculating with the horsepower, no? So there I'm saying about a small example. So there is some maximum capacity of the horse. Okay, maximum speed of the horse. You can't exceed that. Well, see, whatever the thing you give, you can't exceed the speed of the horse. Okay, if it is running at 120 kilometer per hour, it will run at 120 only. It can run minimum speed also 100, 80, 70 and all, it can run, but it will not go beyond that because the capacity of that particular horse is 120 only. Okay, so whatever the thing you can beat, everything you can do, but it should not it will not run beyond that speed. Okay, like that only the generator whatever the, based on the design. design, you should not run. If you are running with a very minimum speed, say for example, in the nameplate details, they have mentioned like you have to run at this much, but you are running very low speed now. So then in that scenario also, the losses might be more, efficiency will be very less. Okay, so in that particular efficiency, you are spending more water. Okay, more water is coming from the upper part of the dam. Okay, upper stage of the dam to the lower stage of the dam. Okay, you are wasting the water and everything with if you are running with a low speed. Okay, efficiency you will not get. So efficiency you will not get na, that is of no use. Whatever the generation that is happening, that is of no use. Okay, so there should be some minimum speed, and you should not exceed the maximum speed also. If you exceed the maximum speed, so automatically your alarm, everything, your sensor, everything will glow on. Okay, the speed is exceeding like that. But even though penstock will not give that much pressure, because penstock size is there, the size is there. But even though I am telling about extreme condition, okay, extreme condition, you have to on the other stage of the instead of giving more pressure, you have to on so another stage, like another 100 megawatt and another 200 megawatt, like that you need to on. You should not overburden your generator. You can overburden, like one certain limit is there, that is also tolerance limit that will be given in the generator itself. Okay, some 5 megawatt, 10 megawatt you can go up to. Okay, 100 megawatt now you can go up to 109 and 110, like that. So maximum they will not run like that, but you can go up to 110 megawatt. So and also minimum megawatt, minimum megawatt generation also, like 80 megawatt you can go up. Some limit will be there, it depends on the generator to generator. So within that limit only you need to generate, otherwise the whole efficiency, everything will be getting loss. You will loss only, efficiency you will be very less. So you are spending more amount of water resources, and if you are not getting, means that is of no use. So this is also you have to take taken into